All right, let's continue our conversations on looking at these property tables. And what I want to pick up is what I said in the previous segment when I was closing it off. I said that with introducing of the quality and this table A4 and A5 or A4E and A5E, you will be able to obtain everywhere in the basically this dome, steam dome, as well as inside of the steam dome, anywhere. That's what I said. My was I 100% accurate there? I mean, technically yes, I'm right. But let's say that I am not a nice guy, and in the exam I gave you this degrees. Okay, I gave you something like this, 18 degrees C, and let's say that I'm asking you, and I'm nice. See, I was a bad person. Now I'm a nice person. I'm saying that this x is 1, so you don't have to worry about finding, the x value. Where am I in between those two? I'm saying that hey, you're right over here. Okay. So the question I have for you is, if I'm asking you the specific volume for the saturated vapor state, what is it? Is it 77? Is it 57? The 18 is kind of closer to 20, so is it going to be 57? Or maybe just change it a bit, called 60, No, that's not going to fly. So now I'll show you something, and you know this from actual mathematics. It has nothing to do with thermodynamics. So it's an interpolation. So I need to interpolate between those two. Actually, after I introduce you the formula, I'll solve this so you can see whatever that saturated vapor specific volume is at 18 degrees C. Okay, so I wanna just simply go ahead and say interpolation, and I wanna let you know that then not only A4 and A5, actually it's more important than A6 and A7, as you will see soon. Okay, so let's simply, what I'm doing is, as I said, this is from mathematics, so I want to start with the mathematics. So let's say that I have y-axis and x-axis, right? And let's say that I have 2 points over here, okay? And actually, I want to simply generalize it. I want to call this x1, I want to call this x2, and I want to call this y1, and I want to call this y2, okay? So the interpolation means that I simply draw a line like this, okay? And then I obtain wherever I am at. Let's say that I'm here, right? That will be given to me. In my case, actually let's write it even here. This is 15 degrees C, this is 20 degrees C, and I gave you the 18. That's what I'm interested in. The temperature that I want to deal with is 18. And in this particular case, I wrote it there, but y2 was, okay? So let's say that I'm interested in that point. So let's say this point, right? All right, so what I will do then is, this is a pure math. So what I'm going to write next is absolutely math, nothing to do with thermodynamics. y2 minus y1 divided by x2 minus x1 will be equal to y, and I'm saying that this is y. That's what I'm interested in. Y minus y1 divided by x, that's the value 18 in my case, x1, right? X1. So actually, just to illustrate, I don't want to teach geometry today. I don't feel like it. But if this angle is alpha, this is where I'm coming from, You see that angle, I'm writing the slope of that angle, okay? So they need to be the same because they are on the same line, right? So that's what I'm doing over here. So one thing to highlight here, though, is, okay, this formula will work. It's not going to fail. But I want to highlight in the real thermodynamics case, these y2 and y1 values are not like this. It's actually, like that. Okay, the formula doesn't change. Okay, but it's like this. As I increase my temperature, the specific volume, talking about that one, specific volume. What happens? Look at what happens to the specific volume. It goes down. It was 77 at 15, but when I go to 20, I increase. It becomes 57. Okay. But that's not always the trend. Look at the internal energy. Internal energy increases with temperature. So you need to know what you're doing, but this formula is not going to fail. So I want to do that particular question. Basically, I'm interested in 18 degrees. So if I write this, I will have to write like this. So let's go ahead and delete this so it's easy for me to write right below the side of that. But, so y2 is 57.762 minus 77. It's negative, but it will, work itself out. So you don't have to worry about it. This is 20 minus this is 15, right? So I'm writing for this big triangle, right? The slope. I'm also going to write the slope for this small triangle, which I'm doing over here. So that's going to be what? Well, that's what I'm interested in. The specific volume that I'm interested in minus the value was 77885 5 divided by, now this is going to be, X is given to me as 18, that's the temperature that I'm interested in, minus 15, okay? So you can see there's only one unknown over here, not a big deal. So let me punch this into the calculator, I'll be right back. Okay, I got this to be 64.6112 kilogram per meter cube, okay? So this is something to note. This will come in handy in actually more A6 and A7 that I'm going to start discussing now, okay? Now, let me go back. So I said so far that A4 and A5, let's look here, or A4E and A5E are for saturated water, right? But remember, there is a superheated water and compressed liquid water regions too, as well as saturated ice and water vapor region, okay? And these are given as A6, A7, and A8 respectively, right? So what I'm talking about is superheated vapor over here, compressed liquid over here, or in the last one, I need to tap into this, the solid vapor, right? So basically it's this, you know. So basically we'll see that it's going to start at the triple line, it will be below the triple line in terms of the pressure. But, you know, I have them over here, so I want to refer to it, so probably it will be the next page, yeah. Look at this, this is A6, this says this superheated water, not saturated, superheated water, okay? So this now takes a little different format, and I want to start reading by this, the pressure over here, so this is like one table, this is P is equal to 0.05, P is equal to 0.10 megapascal, it keeps going and going and going. This is the internal energy, enthalpy, entropy, okay? And what is listed over here is the corresponding saturation temperature for given the pressure, okay? Because there's, as we discussed before, if I have the pressures is 0.05 megapascal, I have one single saturation temperature that I have. And you can see over here, the first one is the saturation. Saturation is listed over here as 81, so it doesn't make sense to have 50 because it's not a superheated water, right? The temperature must be about this value to have it superheated by definition. The only thing that may be a deal breaker is, you know, now I may have to do interpolation twice, because you see the pressure, you know, this is discrete. So I have, let's say that I'm giving you 0.08 megapascal. And let's say that I'm giving you 125 Celsius, right? So now you may need to do interpolation twice, but the formula that I gave you is not going to fail. Okay, and I will do one example to illustrate how it is done to ensure that you really learn it. Okay, but I don't know what else to say about the superheated water table. There's not much else to say. You simply, as a table, you look at it, and the hardest thing is the interpolation, to be honest with you. Okay, the next one is the compressed liquid. So it's basically I am right here in this particular case. I'm right here, superheated, compressed liquid. As the name compressed means, I need to have, you know, high pressures. And in reality, what happens is the pressures that I need to apply needs to be fairly high to have a compressed liquid, okay? And they list it over here as the starting point is 5 megapascals, okay? I want to highlight that. It looks very similar to A6, you can see here, right? I have the same, you know, U, H, S, you know, specific volume, right? Temperature is given, same thing, pressure, temperature here, right? So I don't see any difference from that angle, okay? The only thing is it's very high pressure, right? Note that this is 50 times because the one ATM is 100 kilopascal or 0.1 megapascal, right? So this is 50 times of the pressure, okay? So if the question gives you less than 5 megapascal, you know, because that's the starting point, what are you going to do? Are you going to extrapolate over here? No, not really. I'll talk about that in a question that I solve, okay? So you can see how to treat those. Okay, before I forget, let's talk about this A8 too. One thing I want to highlight about A8 is the saturated ice, which is solid, right? And water vapor. So liquid is missing over here. And I discussed this in the previous segment. And what happens is this basically, in terms of the pressure or temperature, the maximum that I'm going to have is a triple line. And I mentioned this is what, you know, T is and the P is. And if you look at A8, actually that's what they start at, right? The temperature and the pressure. And the temperature and pressure needs to be lower than that, and you see it over here, right? So this particular graph is listed, this particular table is listed as a function of temperature, and you can see 0, -2, -4, -6, etc. It keeps going down and down, right? But you know, nothing really too much to talk about over here, but the specific volume, internal energy, enthalpy, entropy, same deal. So you can see, but this time this is not F, this is I, standing for ice. I'm not sure it's clear, so let me write it big. Ice. Okay, this is G, and F is not here because it's not related. I'm not really going to the liquid phase. If you remember, let's not draw it because it's already complicated graph. But if I was going here, then it would be like this, then I go here, then I pass, then I go up, something like that. Okay, so I'm not talking about that. I'm talking about, you know, sublimation, basically, solid vapor phase. Okay, this is not as common, but I just want you to be aware. Okay. Alright, that's gonna do it for me. I actually will next talk about which table to use. Am I gonna use A4, A5, A6, A7, A8? Which one? I'm gonna explain that to you. Okay? Very important segment coming up. Have a great day. Take care.